Okay, so last class, we talked about um, regret minimization, and we saw several algorithms. One was the follow the weighted majority, and then we extended or kind of came up with a different algorithm, which was the multiplicative weights. Okay, and our goal today is to uh, kind of finish up the analysis of multiplicative weights method, kind of try and understand why does it work. And in some sense, the analysis is going to be simpler given what we've already done. We will do the same exact calculations again, set up a potential function, get a lower bound, get an upper bound, and compare them. Okay. And then we're going to start talking about uh, kind of an extension of regret minimization framework, which is much more common, or not much more, but definitely more common in many real world applications. And this is to bandit learning problem. Okay, and we'll study a very simple but still useful case of it called stochastic bandits, and see one very natural and popular algorithm called the upper confidence bound algorithm. Okay, so it's a lot to do, but we'll see how far we get there. And just a reminder, homework 1 is due today, okay, at 10 p.m. So, and it's on Gradescope, so the server will close. So if you just submit it on time, okay? All right. Let me copy the algorithm if I can. Okay, so this was the multiplicative weights algorithm. It's called method because, more or less there's a lot of variability in how you implement these exact things. And let me just say a couple of things. If you look at this update here, we're saying whenever, if you don't make a mistake, you keep the weight the same. If you make a mistake, you hit it with a multiplicative factor, right? And you can relax it a little bit to account for cases when maybe your loss is not 0 or 1. It's not as if each expert is correct or completely wrong. Maybe it could be something like this expert gets a loss of 0.9, this expert gets a loss of 0.1, and so on. How would you potentially extend this to this setting? Let's say I want to accommodate losses which are not necessarily just 0 or 1 value, but can be any number between 0 and. What are some natural ways to extend? Exactly. There are different versions. You can try, the power is a little bit cumbersome just to analyze it. So instead of, the suggestion was 1 minus eta to the L, the loss, which kind of, becomes this. The loss is 0, it's just a, no factor. If the loss is 1, then you get something like this, right? Just for ease of analysis, the one that's more commonly studied is to set something like this. Okay, it's called exponential weights method sometimes, exponential update, but it's really just the same thing in that I'm multiplying the weight with some factor. If the loss is 0, no change is happening. If the loss is 1, it's more or less like this algorithm, but instead of 1 minus eta, you have e to the minus eta. And it makes tracking the, when you multiply exponentials, it becomes sum in the exponent, so it's easier, that's all, okay? This is just a variant. Another variant is to do okay, this also kind of, is a different way to capture the same formula. If the loss is 0, nothing's happening. If the loss is 1, you recover the 1 minus 8. Okay? All of these things give you back the exact same analysis, right? In exact same bounds. I would say, in some sense, the exponential one is more versatile. It's a little bit easier to work with analytically, but, it just gives the same bound. Okay? So just keep that in mind. Even though I'm presenting it as one method, really there are many, many different methods which you can use the same thing for. Okay. And the main theorem that we stated was that multiplicative weights method can give us our first no regret algorithm. Okay, so this is what we want to say. The expected loss is very close to the optimal loss with an additive loss. Okay, and as I said, the idea behind the analysis is exactly the same thing. We're going to define a potential function which keeps track of how well the whole system is doing. How well are all the experts doing? How well are we doing? Okay. And the potential function, once again, is just the sum of the weights. At any time t, look at all of the experts, add up all of their weights. Okay. So just add up all of the weights. If all of the experts are very, very wrong all the time, then these weights should be very small. So the potential would be very low. Okay. All right. And then we just have to go through the calculations of how the weight updates and so on. Right. So let's just recall some notation. So we have L of t comma I is loss incurred by expert I on day t, right? Okay. And just to make it analytically easier, we can write these two updates into one equation, which is just okay. Instead of having a case analysis, I can write down the update more compactly in this form. If the loss is 0, no change. If the loss is 1, you get hit with the multiplicative factor. Okay. So we just, we know the exact way the loss is changing. The weights are changing. So the way the weights change is a deterministic process. These numbers are evolving strictly just based on how how the experts are performing, the weights. Whereas what the algorithm is doing is random, right? It makes a prediction based on picking a random expert. Okay. All right. So let's, what do we want to control? We want to control the total loss that we incur. Okay. So we will analyze, the loss per single day. So the expected loss of MWM on day t. Okay. So how much loss do we incur? Well, we're going to pick each expert with some probability, right? So what's the expected loss? It's going to be, we have D experts. What's the chance that we pick expert 1 times the loss incurred by that expert, right? And so on. So there's certain probability of picking the ith expert, and once we pick that expert incurs some loss. So our expected loss will just be the product of these things. Okay. And the probabilities, they come from this precise form. They're proportional to the weights. So we just plug that in. All right, so all of this is kind of exact formulas. Now we can write this in a simpler way as just phi of t minus 1, right? So sum of all the weights in the previous day is just a potential from the previous round. So I can simplify it and write this as equals 1 over phi of t minus 1 times this guy. Okay. All right. So now this is the loss incurred by MWM. So the expected loss on day t, right? So let me just give it a name so that we have something concrete. So let me just call it L hour of t. Okay, so this is the loss, the expected loss that we incur on day t. And the next thing that we're going to do is connect it to how the weight evolves. And once again, this is just following the definition of the weights. Okay. You can exactly track how the total potential is changing based on how much loss you are incurring. If our expected loss is high, then the total potential is decreasing a lot. If your expected loss is not too high, then the potential is not changing too much. Okay. And why is this true? We have to just follow the definitions. So the potential on day t is sum of all of the weights on day t. And what do we know about these weights? They evolve based on the losses. Okay, so if these were the weights the previous day, the next day the weights get hit with a multiplicative factor depending on the loss. So let's just substitute that. I can break this up in this way. Okay. All right. And this expression is just the potential from the previous day. And how about this complicated looking thing, the weights times the loss? Well, as it turned out, we just saw that expression exactly here, right? So just substituting that in, we get this eta times phi of t minus 1 times L out. Okay, the loss, the expected loss that we incur was this divided by the total weight. So the sum is just this much. Okay. So even though there is a lot of randomness in the algorithm, the evolution of the algorithm in expectation is very nice. It's just the total weight is getting hit with this multiplicative factor. Okay. All right. And one thing I want to do now, again, this is just for convenience more than anything, is simplify this to say this is at most e to the eta times L. Okay. So here I'm using the formula that 1 minus x is less than or equal to e to the minus x as long as x is greater than or equal to 0. Okay. So the reason to do this is when we multiply this stuff out, multiplying exponentials is easier to keep track. Okay. All right. So we have some upper bound. You know, every time if our expected loss is high, the weights are decreasing quite a bit, right? Which has the same structure as we did before. We also need a lower bound on the potential. So how can I get a lower bound on the potential? Well, just as before, if there is one expert who's doing well, that expert's contribution itself will certify that the potential isn't too low, right? So intuitively, the potential helps track of how well all of the experts are doing. And that is exactly what we're going to do. Okay, if L star is the loss of the best expert by day t, then that gives us a good lower bound on the potential. Okay. And why is this? Well, just from the definition, the weight of any expert is just the total loss incurred by that expert. Okay. So they all start with a weight of 1. Every time they make a mistake, it gets multiplied with 1 minus 8, right? So if they make a total of L mistakes, then their weight is going to be hit with a 1 minus 8 to the power L factor. Okay. So phi of t is at least the weight of the best expert because it's the sum of all of the weights. Which is exactly this much. Okay. And now we are done. We just need to sort of do some arithmetic to compare the things. So putting everything together. Okay, so the loss we incur in day t times the previous loss. We keep iterating this every day. We get the loss on day t times e to the minus eta times the loss on day t minus 1, and so on, all the way up to phi of z. Okay. Which, this was a reason to switch to exponentials, because when you multiply exponentials, it just becomes sum on the thing. The loss we incur on day 1, the loss we incur on day 2, the loss we incur on day t times b. Okay. So which is our total loss. So we just have this very nice inequality everywhere. So this is our total loss. Okay. So the punchline is we have the following relation between the loss of the best expert and the loss that the multiplicative weights algorithm is, which is very similar to what we had for the follow the weighted majority and so on, but except we have 1 minus eta here and eta instead of some fixed constants. Okay. And now you just have to simplify it. You take the logs. Okay, let's take the natural logarithm on both sides. And we are at our final. So the expected loss that we get is related to the loss of the best expert up to this additive term. Okay. We still have this sort of unwieldy looking expression, ln of 1 over 1 minus eta divided by eta looks kind of messy, but there's a simple, we can simplify it by just noting that as long as the step size is not too big, this ratio is pretty small. And you can prove this by just looking at the Taylor series or just plotting it or whatever you want. Okay. So we just take that for granted and we get our final claim that we wanted to prove. So the expected loss of the multiplicative weights algorithm after t days is at most 1 plus eta times the loss of the best expert plus some additive. Okay. And you can, even though we don't know the exact loss and how many days we're going to run it, but if you did, you can try and optimize what's the best choice of eta to choose. Right? And the best choice turns out to be something like square root of ln d by t. Okay. So this 1 over square root t actually, should remind you of something that we saw in eta grad, and it's kind of a similar thing that shows up here. All right, so if you plug this particular thing as a corollary, we get okay. All right, any questions? So this, basically finishes an analysis of multiplicative weights. So we got our first sort of no regret algorithm. So remember, no regret meant that the gap from the best algorithm is going to 0 on average, right? So as t goes on, as you keep playing the game more and more days, the ratio of the gap divided by the number of days is going to 0. Okay. Which is a desirable. You don't want it to be a fixed constant. As you play more and more, you want to converge on the best expert. Okay. Any other questions? All right. So let me say a few things about multiplicative weights before moving on. And so we talked about multiplicative weights just for the context of regret minimization in the learning with expert framework. But actually, it gets used, as I said, many, many different fields. So in learning itself, things that we haven't seen or how it's used for online, like, portfolio management, let's say. You can also use it to do online learning, even when you don't have any experts, right? So one great thing and one important reason why this algorithm appears in very many different places is that it's so general. You're allowed to make up your own experts as you go along, okay? Even in contexts where there's no learning with experts framework, you can cast a traditional learning problem like for example, the online learning problem that we saw, which led to the perceptron algorithm in this specific framework. I can imagine each coordinate as an expert and so on and so forth. You can play these games virtually and then come up with an algorithm which you then deploy and see some things. Okay. In fact, I've done this in my own research in learning graphical models and many other things. And that's the other thing, something like graphical models. All right. And one very important angle that we are not going to explore, but is perhaps equally important, is that along with learning, multiplicative weights also plays a central role in optimization. Okay. You can forget about the whole of learning as a motivation if you're just trying to optimize some function. We saw gradient descent. We saw stochastic gradient descent. We saw Nestrov's accelerated gradient descent and so on. You can actually think of multiplicative weights also a kind of gradient descent algorithm, especially in the context where you're optimizing over probability distributions. Okay. And there, you can think of it as some kind of multiplicative gradient descent, where in gradient descent, given a current set of parameters, we update them additively by the gradient. You can consider a version where you multiply each coordinate. And if you do that, you recover the multiplicative weights method, and then use this for analysis and doing all kinds of optimization things. For example, you can use it to give an algorithm for solving linear programs. For solving semi-definite programs and so on. Okay, so there's a whole area which just explores multiplicative weights as a method to optimize functions without anything to do with learning. And of course, we're not going to study that, but definitely an important application. And finally, in the context of learning, one really important application is boosting. Right? And this also is something that we're not going to cover, but boosting essentially means that suppose I have the ability to build a model which is maybe 55% accurate. I'm trying to predict cats or dogs, but I have a base model which can give me 55% accuracy. Can I somehow just use this and tweak it, or maybe change the data set or do something like that to boost the accuracy all the way to 99%? Can I do that? Surprisingly, you can. And that's called boosting. You're going to combine weak learners, like each one, let's say, gets 55% accuracy, and combine them in some suitable way to get 99% accuracy. Okay. So for example, let's say, let's say every one of you has 55% confidence in guessing, whether it's going to rain tomorrow. Right? So one way to boost my accuracy is to aggregate all of your predictions and maybe take the majority. Right? Intuitively, that should be more accurate than each individual's prediction. Yes? But there are cases where it won't be. Can you think of a case where it won't really boost the accuracy? Exactly. Then you're not going to do that, right? So how do you do it? Even if you know that in general, how can you do it? Okay. So there is a very nice framework for doing it. And there you can actually just use multiplicative weights framework. There's no learning with experts or anything like that, but you can set up a virtual learning with experts game and then use the multiplicative weights algorithm to recover boosting, which is one of the most important algorithms in learning theory. Tons of applications. and it's won several awards as well. The paper that introduced. Okay. And just to kind of, maybe give a punchline, as long as you assume that there is some sort of independence across the different voters, right? It's like predicting, if I'm saying that every one of you is getting 55% accuracy, but everyone is looking at the same app, then taking the majority is not going to help me, right? But as long as you can ensure that the different sort of people have different mistakes potentially, then you can boost it. All right. Okay. So, last year I did boosting, but this year I wanted to do a new topic, a different topic. So we're not going to do this. Okay. Instead, what we're going to talk about is what's called bandit learning. Okay. But before I do that, let me do something else. Which is to show you something. Okay, so we saw the infallible expert case where somehow if you run the follow the weighted majority or follow the majority, it does quite well. So you can also visualize multiplicative weights, right? So the updates are very simple. You're just making a multiplicative hit on the weight. And you can check how the cumulative loss and the expert probabilities change, right? So initially on day one, every expert, let's say we have 5 experts, every expert has just a weight 1. Okay, so initially every expert has just a weight of 1, and the probability that we pick each expert is exactly just 20%, 1/5, right? So it's proportional to the weight of that expert divided, it's equal to weight of that expert divided by the total weight, which is 1/5. Okay, everyone is equally likely. And then we run the game. And you can see the experts start kind of differentiating themselves. Actually, it's better to, okay. So these are the losses and the probabilities, they're slightly diverging from 20%, which was kind of, when there was no information, right? But there's not much of a difference between the experts here, right? And the reason for that is the step size, the learning rate is very small. And, we can change it. So let's say I increase it a lot. So meaning somehow each mistake is going to hit you with a much bigger penalty. Okay. So the losses, they are kind of the same, they're doing their own thing, but the expert probabilities that we assign are really splitting apart, right? So the red expert is not doing very well, has very low probability. The orange expert was doing well, but somehow the green one overtook it. Okay. And you can see in the end, the loss of the green expert is lower, and the probability of picking the green expert is the highest. Okay. So you can just kind of change the learning rate and immediately see how it changes. You don't want it to be going above 0.5 because then I think it'll just run into 0 errors pretty soon. Okay. All right. So it's a simple way to visualize what's happened. We are really splitting the experts apart based on the historical performance so far. Okay. All right. So that's a quick demo of what can happen. Okay, so now let's talk about bandit learning, right? Okay, so let's recall the setup of learning with experts. And so we had these experts who were making predictions, and our only input was about how these experts do, and then we had to kind of pick the expert for the next day and so on, right? But in the way we are approaching the algorithm, so imagine that I pick expert one, right? Then I get information about what expert one predicted. But at the same time, we're also making a big assumption that we also see how all of the other experts did, even though we did not pick them. Okay. So imagine, you can think of two cases. One, which is I think a little less concerning, but still a problem, is every time you ask an expert for a prediction, they charge you $1. Right? You have some subscription fee. I have to subscribe to this newsletter. I have to subscribe to that newsletter. And then eventually I'm going to aggregate and follow one expert on each day. But no matter what expert I picked, I'm still, if I want to get the information about how the other experts are doing, which I need to run multiplicative weights, right? I need to track their behavior. Then I have to know what they predicted or how much loss they incurred. Okay. So we made two big assumptions. One, we know the losses or rewards of all the experts. Okay. And I'm not entirely sure why. Maybe it makes some sense, but in the whole of literature in bandits, people talk about rewards instead of losses. So I'm going to switch to rewards, but it's really the same thing, right? Instead of saying that I don't want to, incur a loss, I want to maximize my rewards. Okay. And can you imagine scenarios where this is too strong an assumption? Maybe if it's like a subscription fee, I'm still willing to pay the fee, but sometimes I want to say you don't even have that. It's not just like I can pay a fee and get the expert prediction. Can you think of scenarios where that can happen? It really happens every time, many times. Let's say you're using at least one of the apps that you use every day. Do you use Google Maps? Right? So think of the scenario where it says go left or go right. You take only one way, right? So it is going to aggregate historical data and telling you, okay, go left or right at some point. But each day, you only see the reward of taking one of the outcomes. Okay. So that's sort of, the reason it's called bandit actually, I think comes from, so let's get rid of, or, okay, so this is a very strong assumption. Knowing all of the losses or rewards. Okay. Now, we can consider a scenario which is, the traditional example taken is you have slot machines. I know. Okay, but you have slot machines, and just imagine that can really be a traffic app. You have k choices to make. Go, take this street, that street, this street, that street, and so on, right? You have certain number of choices to make. You have choice one, choice two, so on, all the way up to choice D. Okay, so these are technically our experts, but now we are thinking of them as choices that we have to make. And when I pick choice one, I get some reward. When I pick choice 10, I get some reward, and so on, right? But when I pull, if it's like a slot machine, I press this button, I get something. If I press this button, I don't get anything, and so on, right? But when I choose a button, I don't get to know what I would have gotten that day for the other buttons, right? So in some sense, the limitation is that you get to see the reward or loss for only the expert that you pick, only the path that you chose to take. Okay, the maps analogy I like better because you really, let's say you're trying to build some kind of dynamic navigation or directions app which takes traffic into account, right? Now at certain time, 4 p.m., it says go on Wilshire. Okay, but another day it says go on Westwood. You only pick one of those options. You don't know what's the reward for picking the other option if you hadn't. Okay, so so that's the main challenge that we are going to overcome with our framework, which is partial feedback about choices or experts. And in the most extreme case, we only get to see the loss or reward of the expert that we pick, and that's it. Okay. So we only see the outcome, that is loss or reward, for the action we took. We don't see the losses or rewards of the actions or choices that we did not take. Okay? Make sense? So this is called the multi-armed bandit problem. Meaning, again, the analogy comes from this sort of slot machines where you have a slot machine with D different levers. Every time you pull a lever, you get a reward, and you're trying to figure out which, which lever to pull over time. Okay. All right. So this makes the problem much harder. We never get to see the rewards of all the other people we did not choose. Okay. To make it a little bit easier, we are going to change the adversarial nature of the rewards a little. Okay. Again, you can study, there are various works, you can teach a full course just based on bandit learning. We're not going to do that. We're going to focus on a special case, which will help us learn something about the problem. Okay. So the simplifying assumption that we are going to make is that of stochastic bandits. Okay. And what's the stochastic bandits assumption? So when we talked about learning with experts, the loss of each expert, we made no assumption about it whatsoever. It was just given by the experiment, by the environment, and we just had to match the loss of the best expert. They could be terrible, that's fine. We just had to match it. The experts could be flip-flopping all, every other day or every 10 days. They could be completely inconsistent. Just a single expert, that's fine. We still had to match the loss of the best expert. So we made the problem a little bit harder by saying that we don't get to see the outcomes of the experts. But now when you don't even see the outcomes, if you don't make the second assumption, it's going to become very difficult, right? It could be that every day we see the loss of one expert and every other expert had a loss of 0. Every expert that we pick, the loss is very high. Then there's no way to do better. There's no clever algorithm you can come up with. Okay. So because we're not seeing the rewards, we need to enforce some consistency even among the unseen rewards. And the natural way to do that, would be to assume there is some probability distribution for the reward. Okay. So this is called stochastic bandits, meaning on each day, or let's say each expert or choice has a reward distribution. Okay, let's call it PI. Okay, this is just some real number. And, again, I'm going to be as general. You can just think of it as a number. Reward means that we are trying to maximize it, but it could be negative. It's just loss or reward is fine. As I said, the literation bandits typically uses reward. So let's use that, right? So let's say pick arm 1, you get some reward. Like, maybe you'll get a reward of $1 with probability half. And then, maybe you'll get 50 cents with probability 1/4, and maybe you get 0 with probability 1/4. That's lever 1. Lever 2 is maybe you get $2 with probability 1/10, right? But maybe 0 with the rest of the probability, and so on. Okay, so there's a fixed distribution. This is what enforces some consistency, even though we don't see the values. And each day T is a sample from PI, is an independent sample. Okay, does it make sense? So the game is you have D choices as before. Each one has their own distribution. You don't know the distribution. Of course, if you did, then there would, everything would be solved. We don't know the distribution, right? So maybe, first day I don't know anything. So I pick, let's say I choose this expert. If I choose expert 1, then I get to observe the reward of expert 1. That's it. I don't see any other information. So maybe I get reward of, like, let's say 0.8. And then next day, maybe I choose this expert. I see 10. This is day 1, day 2. All right. I don't even observe, what happened with expert 1 here. I only see one value here. And these are all unknown. Maybe I think, oh, this is great. This expert did well, so I follow that person, and then he gets 0.5. Now what do? Maybe you go back to choice 1 or something like that. Okay, so this is the basic setup. And what are we trying to maximize? We are once again trying to maximize or, basically minimize our regret. right? So you want to minimize the gap between our performance and the performance of the best expert in hindsight. Okay. And the performance of the best expert will also be something stochastic. It depends on the distribution, but not on the exact realization, right? Because we don't even see this question marks, right? So it should depend only on the distribution. Okay. So let me just formally define it, and we'll talk about some examples that show up in real use cases, and then we'll see. Okay. All right. So what's the setup? Formally, we have de-armed bandits. Armed really corresponds to this lever analogy, and we have distributions P1 through PD. Okay. And think of these are just real valued distributions, univariate real valued distributions. Okay. And each distribution has a certain mean. Mu I is the mean of distribution Pi. Right. So this is what the ith choice will give us in expectation. So in some sense, this is a true reward of that expert. We don't know what this value is. If we knew, then we would just go for it, right? So going back to this analogy, maybe this last choice is the one which has a high expected reward. Maybe it has an expected reward of 100, but we don't know because we never pulled that lever. Okay. So there's a mean of distribution this much, right? And now we have our agent, aka our algorithm. So as our algorithm, our agent has to make one of these choices. And on each day, okay, so we choose an arm, we choose an expert to follow, right? So we don't get to decide anything else. We just get to see which expert to follow. And let me denote it as IT, which is a number from 1 through D. Okay. And then, the environment shows us reward or RT, which is sample from the distribution that we picked. Okay, so we see a particular reward that this particular arm, this particular choice got on that day. All right. Okay. And so this is a game. Every time we pull, we get some information, the reward, and then we go on. All right. And what should the goal be? You can come up with various objectives depending on the context, but the most sort of natural and generic goal is to minimize the gap, right? Just as we did for multiplicative weights, right? But except here, the regret is not going to be the actual regret, but the expected regret, right? So goal is to minimize the gap to best choice, right? And so this is going to be, I'll just write it down in a second. Okay, so let's understand this. So this is just the expected regret our algorithm got. On day one, I picked index I1, so I got reward Ri1. On day two, I picked index I2, so I got Ri2 and so on. Okay, these are the specific ARM choices that we made and the rewards that they got. So there's two sources of randomness. One, the choice that we make could be randomized, right? The index could be randomized. Maybe with probability half, I pick choice one, expert choice one. With probability half, I pick choice two. The other source of randomness is the reward itself, right? So we are in the stochastic setting where the rewards are coming from some distribution. They're not deterministic. So we have some control on how they are being generated. Okay. So this is the expected reward that we get. And T times mu star is just if I followed the best expert, right? So where mu star is the highest, is the best choice. Right? Yeah. So it can, in fact, in the algorithms, it would, right? So in the objective, it's not. Okay, you can take that into account too, right? So right now we're going for the simplest goal, and the simplest goal is to match it in expectation, right? The second thing would be to say, maybe I want to match it in expectation while also not have like wild variance. Okay, but getting a higher expectation should be the first thing to do, right? Okay, so this is a problem setup now. So we don't know what the distributions are. Maybe you can assume they're coming from some families, some parametric families, but ideally you wouldn't even do that. But we'll do that just to get some algorithms and then see where we can go from there. Okay. Any questions about the setup? And just as before, the goal is to minimize this regret. And ideally, no regret means that the ratio of this goes to 0 as time goes. Okay. All right. So that compared to multiplicative weights framework and learning with experts, once you get to bandit setting, there's an immediate sort of dichotomy that arises in any algorithm. Right? So just go back to this setting, right? So maybe when I pick choice 1, I got 0.8, choice 2, I got 10, and this was like, maybe again 9, and so on, right? So one thing you can do is just follow the expert with the best sort of reward that we've seen so far, right? But there's a problem with that. What's the problem with that? Yeah, exactly, right? So on the other hand, if we keep flip-flopping and trying things that we don't, then we might miss out on what we already have in hand. Okay? And this is an important theme. You have to balance these two. And this leads to what's called as the exploration versus exploitation strategies. Okay. Exploration means that somehow we do want to try new choices. They could be really terrible and we'll incur some loss of revenue if we do that. But on the other hand, if we don't explore, kind of take this risk, we won't even know if there are better options out there. In fact, in the early days of something like Waze, it would have some guinea pigs. Basically, it would just send people on things it knows are not probably good routes because it needs the information. Okay, now, of course, a lot of it is completely mapped out and there's so many cars that you don't, but it would send people on this sort of exploratory routes so that it gains information. Okay. So even if I'm getting very good rewards with choices 1 and 2, at some point I should really venture out and try the other ones. Okay, that's the exploration part. Exploitation is just use the information that we have and make guesses. Right, at some point, maybe you have very good confidence that, okay, expert 1, the reward is like 10, expert 2's reward is 5, and so on and so forth. Then you can just make a choice based on what you already know. Okay. So one of the challenges that shows up in bandit learning, and I think this is why it's important as a toy problem, is because this sort of dichotomy or this dilemma shows up in many, many practical places. Okay. All right. So let's, can you think of some examples where either the banded problem or even this conceptual thing of exploration versus exploitation actually shows up? It can be learning, it could be practical systems, whatever you can think of. Any applications that come to mind where, some of them, they definitely use bandit-based stuff, but not the simple stuff that we're going to look at. Okay, there are two simplifying assumptions. One, right now, the distributions are not changing based on time. You can get rid of that. Okay. And the distributions, these are called, there's something called contextual bandits, where it can depend on the time. It can also depend on something that I store and so on. Okay. But even in the simple setup, it shows up in many places. Can you think of some example applications where it might be useful? This particular framework. Any guesses? Well, one thing I already mentioned, so I'm just going to do it, is dynamic traffic. Right? So you don't get the information about the routes that you didn't take, but you still want to make these things over time. Okay. Of course, it's not exactly as simple as we stated because there's context involved. Right? So there's something called contextual bandits. It could depend on what car I have. Am I going in a car or a bicycle or anything like that? Okay. What else? Any other applications come to mind where you might face similar scenarios? No guesses? Mm-hmm. Right. So you can think of, basically choosing which option to choose. Choosing which option to show. Okay. In the same vein, in fact, a much bigger scale problem, both economically and infrastructurally, of the same thing is for online apps. Okay. And let me put this in parentheses and say, one of the biggest thing is online ad display. Right. And here it's definitely like a bandit setting. I might have a million ads and I show you only one of them. I'm not going to say, okay, rate this ad, rate this ad, rate this ad, and so on. You'll probably never use my service if I do that, right? But it's not exactly one. Maybe I show 5, right? But it's still a small sample, the same situation. I might have 5 ads that I show, and you click on one of them. So that's my reward. The algorithm is like Google, right? I'm the environment or something. Okay. So now you can imagine you can have contextual bandits where the environment can have information about my location, my age, and other demographic information. Right. So you can put that into some of the setup. This will be the next sort of refined model. Okay. But even with this basic model, it captures some elements of online ad display that we are only shown a few ads, So you only know the rewards of a few things. Okay. And even there, they definitely use some variants of these bandit algorithms to explore and exploit. What else? Yeah. Yeah. That's definitely, do you always keep eating at the place which has consistently best food, or you want to try out new stuff? And one very important place where this shows up, and of course, there are a lot more guardrails there, is adaptive clinical trials. Okay, and this is a setting where you definitely have the same situation, right? So I might have 10 different drug choices, but really you only get to see the reward for taking one particular drug. You don't get to see what would have happened if I'd taken those other 9 things. You cannot do that. So you know, uh, I think it's much easier to experiment in these things because of the scale and the other constraints, but the same sort of problem shows up here. There is this exploration versus exploitation thing that you have to play with. Okay. And people have used some form of bandit algorithms to allocate people to trials. Right? So you can think of each day as like, each new person as like a new day's worth of data. You put that person in one particular treatment, the different treatments would be the different choices, right? And you get some reward, you get to know that. And at some point, you have to draw the line. Okay, I have to try this new treatment versus I have this other treatments which are doing okay. Is it ethical, or is it an expected reward wise okay to allocate this new person not to the trial that I know has the best reward so far, but something new? Okay, you have to balance these things. All right. So all of these things are really important problems which are which have the same element, like bandit stochastic information. Okay, we have incomplete information. To get around that, we assume some kind of stochasticity in the rewards, and then we have to do more. Okay. And lastly, one reason which I think is it has received so much attention is that is the simplest non-trivial reinforcement learning problem. Okay. And if you know what reinforcement learning is, that's okay. If you don't, it's basically like saying, I'm a robot, I'm trying to navigate some environment, or you could be a model where I'm trying to make, give out some output. Okay. And here you definitely face the scenario that you don't get to see the rewards of making all of the different choices, right? You only see the reward of the choices that you take, but then you have to still make the choice, right? And it's the simplest setting in that we are assuming there is no state involved. There is no memory from day 1 to day 2. Okay, that's the biggest difference. If you're a robot, then I make some choice, then maybe now I'm stuck uphill, right? So there's some state that goes with the day that you're in, and then the rewards change based on that. Okay. So if you were to draw a concrete analogy, in RL, we talk about agents, which are basically like the bandit algorithm for us. You talk about environment, which is, system giving rewards, right? And actions are just choices. Rewards are rewards. And policy is just the algorithm for choosing actions. Okay. So the biggest difference which differentiates it from the full-blown reinforcement problem is that we are assuming there is no state, meaning when I take an action, it doesn't change my own state. Okay, if you're a robot, if I decide to bend down and pick something, I bend down. Now my state is not the same. Something has happened because of the action that I took, right? So that's something to do. So in some sense, no state in MAB. MAB is the multi-arm bandit problem. So the multi-arm bandit problem is basically like the reinforcement learning problem, with the biggest difference being there's no state. There's no memory from the different days. Okay. So given that we're making such a big simplification, it's still useful. Even though we're making such a big simplification, it's still useful because you need to handle this case. And the algorithms developed here have been used for full-blown RL application. Okay. All right, so that's kind of the introduction to bandit learning problem and how it generalizes the learning with experts framework. And tons of real world applications, especially when you soup it up a little bit. Maybe you add some context to the state, even if the state doesn't change the environment and so on. Okay. All right. So what I want to do for in a little bit of today and the next lecture is talk about two very important algorithms that show up in bandit learning. One is called the upper confidence bound. The other is called Thompson sampling. Okay, the focus is on the algorithms. We will motivate it and kind of study them for a toy case, but they can, once again, be applied in more general. Okay. So the toy case that we are going to study is a very beautiful problem in probability, which is just called Gaussian bandit problem. Okay. And this goes back to the question that was asked, does the variance of the distributions matter? In fact, the distribution matters. Like depending on the distribution, the problem can change a lot. So as a toy problem, just to get us started, in some sense, the simplest distribution that people can think of in these contexts is the Gaussian distribution, right? So that's what we're going to assume. So the assumption is that each reward Ri is sampled from some Gaussian distribution with mean mu I and variance 1. Okay. You can also change the variance. I'm simplifying it so that we can understand the algorithm. And when you don't have the, this variance assumption, you can tweak it to general variances. Right. So the picture you should keep in mind is somehow, we have choice 1, okay, so we have D choices as before, and each choice has a hidden mean inside it, hidden average. It's coming from some Gaussian distribution. So this is Gaussian with mean mu I. Okay. So for example, maybe choice 1 has a mean of 10. Maybe this has mean of 5. Maybe this is negative -3. Maybe this is 17. Maybe this is 100. Okay, these are the means, not the exact rewards that you would get, but the reward that you would get in expectation. Right? And I also made the problem simpler by assuming that the variance of all of them is just 1. Okay. You can get rid of that, but let's just keep it for now. So meaning probability reward equals R is e to the the exact form is not important. We're going to use some meta properties of Gaussian which make it all work. Is all you really need is like some bound on the variance and some tail bounds. Okay. So on one day it could be 10, the other day it could actually be 7, it could be 4. Right? On an unlucky day, even if your mean is very high, you could see a low value. Okay. It's unlikely, but you could see a potentially low value. Okay. So we made two simplifications. One, we assume that the unknown distributions are Gaussian. And we also assume that the unknown distributions, they all have the same variance, right? You can get rid of the second, assumption reasonably well, and the first assumption also in some cases. Oh yeah, you're right. There's no pi there. Okay, good. All right. So, and what is our goal? Goal is to minimize the gap between okay, so minimize the gap between the reward we see on day t for the choice that we pick. Okay. And the question is, how small a regret can you get? Can you make the regret go to 0 with the ratio, or can you get, can you get square root t as before? Can you make it even smaller, and so on? Okay. All right. So, and as I said, this has been around for a long time. This kind of introduced a while ago. And in general, you cannot get like a bound which doesn't depend on the means. There should be some dependence on the means. If all of the means are the same, for example, your regret will be 0 on average, right? Because you're basically doing very well. So if there is no gap between the different means, your algorithm, in fact, any algorithm is going to do well. If all of the choices are the same, you don't get any extra gains by picking a particularly good choice, right? So it really depends on the gaps, okay? And there's this really clever lower bound from 1985, 1980s, really, Lai and Robbins from 1980s. Okay. So they basically showed that if you have, for any algorithm, if you don't know the means, even in the case where you have variance 1, the regret, so this is the regret, RT. RT has to be like log. It is very good, but they're saying you cannot get 0 regret. So you cannot make this thing go to 0 in the limit. No matter what you do, you at least have to incur some regret. Okay. But it's still very good. In multiplicative weights, we're only getting square root t, whereas here it's like log t. Okay. So, I mean, it seems like we're doing better than multiplicative weights, even though we're getting less information. But remember, we assume stochasticity here. So the rewards are not completely arbitrary. That's what distinguishes it. Okay. So we made the problem a little bit harder by saying we're getting less information about each choice or expert. But we also made it a little bit easier by saying over time, they're all consistent amongst themselves. Okay. And in fact, the exact thing that they showed was something like the regret must be like omega of log t times summation over all experts of the gap between because it depends on the gap. All right. So, the exact lower bound is not important. We'll kind of get this performance anyway, but the point is that there is some lower bound. This has been around since the 80s. All right. And what can we do in terms of coming up with algorithms? Any suggestions? How can I come up with an algorithm here? So what would be a nice algorithm to try? Yeah, so let's try that. Idea one is somehow adapt MWM. Okay. So to adapt it, what do we need? We need some way of if I want to at least use it directly, so some of penalize experts and so on, I need some guess for what the reward would be, right? Yeah, that's basically, you can try that. So somehow give some sort of buffer. Okay. And qualitatively, one thing you can try, and you can make it work, but it gets somewhat messy, is pretend you're running multiplicative weights, right? But to run multiplicative weights, you need to know the rewards. I'm going to guess the reward for the experts that I don't see. Okay, which makes sense. If let's say I ask you to choose, okay, here are the 100 choices. I want to pick the best one today. One natural thing is to guess what's the reward going to be for tomorrow and use that as kind of the actual reward and update map, right? And, you can say somehow for the choose an expert, update weight properly. For the rest, use the past history to guess. Okay. It can work. You have to address other issues like, here we're not assuming that the MUIs are bounded. So the rewards need not be between 0 or 1. What if the loss is like 1,000? Now you have to take that into account a little bit, maybe just scale values in some way and make them all bounded and so on and so forth, right? But you can also get a slippery slope in the sense that if I'm using the past to guess the reward, if I make a mistake the first day, then that can amplify, right? For the other choices that I've not seen any information, I'm using the past guesses, but maybe I picked choice 10 on the first day, and just because of randomness, it got a reward of 2, even though the mean was 5. Now, until I pick that expert again, I'm not going to make any sort of update to my guess for what the mean is, right? So it can kind of, get into a sort of feedback thing where the wrong answer gets even more amplified. Okay? But you can make it work, but it's very cumbersome and not as clean as you would want it. Right? Okay. So that's one. What else can we do? Okay. So there's this beautiful algorithm from early 2000s. So, I mean, I would say it's relatively recent given how long the bandit problem's been around. Right? It's been around for a long time. And multiplicative weights has been around since basically in some form or the other since 60s, 70s, 80s across very different communities, right? But the algorithm that we're going to first discuss is called the upper confidence bound. Or UCB algorithm. All right. And I think it's from 2000 something. Maybe let me just get the exact time. Yeah, so I think it's some 2000 something. And the way to fix multiplicative weights in this way, it's called X3. That's again, a different algorithm, but let's look at UCB, which is I think the simplest and very clean, really beautiful algorithm, right? And it comes with a very simple principle. And so the basic thing is we're going to abandon trying to estimate the rewards of the unknown arms. Okay. If you have seen each arm many times, then I might have a good guess, right? But otherwise, I don't have a good guess, right? But then if I want to see each arm many times, I have to spend many rounds just exploring, which might be too expensive to catch up in regret, right? You have to play this balance. And what UCB does is the following. It's like the most optimistic algorithm that you can think of. And maybe we should learn from it in other parts of life too. But anyway, so what the main principle behind the algorithm is for the arms for which I don't have enough confidence or enough sort of information to say, okay, the mean is actually 10. Maybe for each arm, I've seen one sample. One sample doesn't give me good confidence about the mean, right? If I've seen 100 samples, the average empirical mean should be close. But if I've seen only one, I don't have very good confidence, right? So the optimist view is I'm going to assume that the mean is as high as statistically likely given the observations so far, right? So there's this thing in statistics where you flip the problem, and these are called confidence intervals. So what does confidence interval intuitively mean? Imagine I have a random variable x, which is actually n, some mu comma variance 1. So the mean is mu. It's a Gaussian random variable, but the variance is 1. I see a sample, and the sample says something like, this is 0. The mean, the sample said the sample was 10. Okay. Usually, we know the probability of seeing 10 given the mean is this much. But you can also flip the question, which is, if the mean is 10, what's the chance that mu is something like, 11? What's the chance that the actual mean is 12? What's the chance that the actual mean is 13, and so on and so forth? In some sense, most likely the mean is 10, but that doesn't mean it's actually very likely to be 10. That's the most likely value. But 11 and 10, even if the true mean is 11, seeing 10 is not that unlikely. Okay, so you can put some kind of band for your guess for what the true mean should be. Okay, so 10 has some probability. Given that I see 10, what's the probability of mu being 10? I can estimate that. What's the probability that it's 11? I can estimate that, and so on. Okay, confidence intervals basically tell you what is the chance at what interval you have very high confidence for mu to be. Okay, given one sample, 10, I can look at the entire thing and say, okay, of course it's some number here, or maybe between minus 100 and 100. It's very likely to be in that. But that's too broad a window, too broad an interval. The narrower it is, the better. Okay, so that's the notion of confidence intervals, which have been around in statistics for a long, long time. In fact, whenever you do statistics 101, that's something that gets investigated a lot. Given this particular parameter, what is the confidence interval for this value across the data set and so on, right? So what we're going to do now from optimist perspective is basically ask this question of compute the confidence interval, right? So, let's say, I'll state this math in a second, but so the punchline is choose the arm with the highest possible upper confidence bound. Given the current data. Okay. So meaning, so maybe the math is, I'll get to the math later. Let me just draw a picture. So this is choice 1, 2, and so on. So let's say we have just have 4. Okay. So initially I don't know anything. So let's say I just assume all of them have 0 rewards. It's kind of a bad guess, but maybe let's say I've seen at least one sample from each funnel. Okay. Maybe this sample was here, maybe this was all the way here. And maybe this guy is very close to 0. Okay. So far, these are the empirical means I've seen. Maybe I saw only one sample. So one sample just means that, one sample was here for the first X squared, one sample was all the way here, close to 0, even negative, and so on. Okay. This could be just the samples that we've seen so far or the empirical averages, right? So meaning this is just the average reward for, choice 1 so far. In rounds, we picked 1. Okay, the average is only computed on the rounds that we picked 1. Otherwise, we don't have any information, so we don't take that into account. Okay. So given these are the empirical averages, we can put some confidence on where the true mean can actually be, right? So imagine for this expert, I've tried that expert 100 times and the empirical average is green. So qualitatively, if I were to put this band for where I think the true mean would be, how would that width be? For this expert, I've seen the expert 100 times. So I have much better confidence of the mean. So the band's width would be very small. Okay. So you kind of plot, maybe some kind of window for where the true mean might be based on the samples that we saw and the observed empirical mean. Right? So the width will depend on how many times we chose that particular expert. We repeat the same expert many, many times, we have very good confidence on what the actual mean is. Right? So maybe, but on the other hand, for the purple expert, we saw the expert also many times. So maybe it's something like this, but not as much as green. So maybe it's a little bit broader. You know what? Actually, let me. Okay, so let's say. Okay, something like this. And maybe for the second expert also, we saw that expert many, many samples. So we have a very tiny window of a guess for where the true mean might be. Maybe for the orange expert, we only saw one sample. We set a value of 1, but we have very little confidence on 1. Okay. So the window, which you can figure out from basically the distribution of the Gaussian distribution, there are exact formulas for what this, endpoints would be, you would compute. Okay. And then the optimist strategy is don't go by the history, but go by the best potential value for the true mean. Okay. So this expert had a small value, but I know so little that the potential is this entire yellow band. Right? So you pick the expert with the largest upper confidence bound. Right? So we'll see how to compute this value exactly. So maybe to be explained later. Okay. But the template of the algorithm is the following. So you compute the empirical average, right? And then you compute the upper confidence bound. And we will define it formally in the next lecture as well. Okay, for where we think the true mean could be. If you've seen many examples, the width would be shorter. If you haven't seen many examples, the width would be higher. So for a reason to pick an expert would be the actual reward is very high, like here, or the reward isn't too high, but have a lot of uncertainty, so the upper confidence is high. Okay, so that's the algorithm. Pick the choice with the highest, reasonable value for the unknown. In case it's kind of an optimist view. If a person, if this choice, the true mean can be this high, I'm just going to assume that's the thing. Right? The potential is very high. I'm just going to choose that particular plane. Yeah. Right. So initially you had to just basically spend maybe D rounds to try each one. But the thing is, it gets started as soon as you have at least one sample per user. It doesn't mean like I have to try each user or each choice many, many times. So that's where you gain. You still have to pay in terms of trying each person, or each choice once. But once you have that information, it gets started. Okay. And people have incorporated like, what if I have some prior on the means and so on. So to get around that. Okay. So next lecture, when we come back, we'll make it formal. Like, how do you compute this upper confidence bound? The intuition is that you have an actual empirical value. And depending on how many times I've made this choice before, I can decide how broad this interval has to be, right? The width of this really only depends on how many times you've chosen this particular person. But overall, it's a very convoluted algorithm, right? Because who I choose depends on the things that I've chosen so far. and that the next day can change my confidence. Okay. All right. So we'll make it formal and kind of derive the exact expression. It's a very simple algorithm to implement in the end. Okay. So we'll talk about this on Wednesday. And remember, assignment 1 is due today. All right. Okay. See you all on Wednesday.